So let's dive right into the introduction of Damiaan. Damiaan is working for IBM. He has various different roles as a background. He's been a consultant, an architect, and a developer. And nowadays, from IBM, he's fully dedicated to promoting development and also open source. And the example he'll be giving is about building a coronaradar. And I was just discussing with him when you were all coming in that he has had some really interesting presentations. He joined a panel at Tweakers, and I hope you have a great experience with him walking you through the end-to-end project of how to build such a coronaradar yourself. So please get ready to do some code yourself. He'll be presenting for an hour, and we hope to get you interactive during the hour itself. And afterwards, we have an hour of aftercare where you can ask questions and you can continue doing the code. So without any further ado, let's give the floor to Damiaan.
Right, so if things work here, then you should at least have a look at my Git page right now, which is hosting all the files on GitLab. So that should work. First thing I'll do, I'll share the link with you so you can have a look yourself and maybe even go along. But what I plan to do in this first hour is mainly walking you through all the code there and getting to know what's available. The link is also in the Discord channel, so you should be able to find that. Yeah, I'm going to walk you through and talk you through the code that I've made available there. If you go one folder up, there's lots more because I spent the last 6 months on doing these kind of analyses. So there's a lot of experiments there as well. And a lot of other stuff you might explore, but yeah, beware that this PyData folder is more or less documented, and the rest is typically not documented. Lots of experience and probably stuff that's broken and won't work. So yeah, if you keep to this folder, you should be fine. Right, so yeah, what happened? I've been working in data science, as they call it now. I still don't really like the term, but well, data mining, machine learning, and whatever you want to call it, for the last 25 years. So I'm a computer engineer by origin. I studied artificial intelligence after that, when people were just starting to think about artificial intelligence and seeing it as a potential job, to be honest. I mean, the thinking about artificial intelligence probably started just after during the war with Alan Turing, but and maybe even before. So yeah, at that time it was mostly a philosophy, thinking about what we could do, building very small neural networks consisting of 2 nodes and a hidden layer perhaps. So that's what we were doing. Lots of knowledge-based systems, rules-based systems and stuff. So yeah, basically I joined IBM after that, and I've always been working in that area. So so what happened? Yeah, early this year, yeah, obviously this pandemic broke out. Cases were really starting to rise in China. We were wondering what was going to happen. IBM, when it arrived in Europe and the US, IBM sent us all home to work from our home office. Luckily, I have a good home office, so that helps a lot. And so and at the same time, that was late March, early April. I was wondering about new material for workshops this year, because that's my current job at IBM. I'm what's called a developer advocate. So I do these kind of workshops for people, trying to inspire them to work with this kind of technology. And then hopefully, obviously, because I work at IBM, maybe use some IBM technology there as well. Today, what you will see is all open source. It's all based on freely available libraries. And all the code that you see is also freely available, as should be clear, because it's all available on my Git pages. So yeah, I was wondering about new material for workshops. My wife, who is a nurse, was starting to get very busy at our local hospital in full isolation, daily treating suspected COVID patients at the time. So I was really wondering, what can I do? What can I contribute to this cause? So can I as a data scientist, have a look at this kind of data and find interesting stuff that people can use to mitigate the impact of this whole outbreak. So that is where it started. So first thing was just looking for data. So at the time, There was not that much available, so I found the EU CDC website, which I can show you here. And that's at that time, that was one of the few places where they had a daily update of case data, and in this case, worldwide. Because obviously I wanted to say something about the Dutch situation. I would really like to help out here, more or less. And as a side project for getting interesting workshop material. But then I thought, yeah, I want to understand the nature of disease outbreaks and how does that work and how can you model that, or can you say anything about it in prediction or projection of progress of a disease outbreak. Then I thought, yeah, what I have to do and what you should do as a data scientist is not just look at the Dutch situation, because then you get a picture and maybe a totally overfitted picture of the Dutch situation. You can easily build a model that fits the Dutch outbreak perfectly, but it doesn't generalize most of the time. So yeah, thinking about overfitting, I thought, yeah, I need to go and have a look at as many outbreaks as I can. Because if you can find some similarities between outbreaks in South Korea and Finland and Iceland and South America, Brazil, for example, then yeah, if there's similarity there, then there's probably that's some kind of ground truth. Then you can generalize over those outbreaks. So I started off with that data set. Yeah, so what I do now and what I still do daily is just download this data set, which is available as an Excel file and also as a CSV file. At the time, the CSV file was pretty unstable, to be honest. I had all kinds of problems where suddenly all columns were, there were no commas anymore, and stuff wasn't quoted properly, or suddenly quoted, and then the day after it wasn't. So I got used to using the Excel file, which is available there, luckily in XLSX format. But now I can probably switch back to the CSV file. It wouldn't be such a problem. So if you want to use the CSV file, it's also available there. There's the link here where you can download it, and you would be able easily to change the code that I've available for you to use the CSV file. Because yeah, Excel files can be tricky. You've probably seen this one just in the news, where lots of UK cases weren't reported properly, and they blame Excel, but yeah, they should probably blame themselves, because what they did is they used the old XLS format, not the XLSX format, where you can only have 65,536 rows in an Excel sheet. So so they uploaded from CSV files locally into that Excel format, and then lots of rows got lost. So lots of people weren't paying attention, and I don't think it's really you shouldn't blame Excel, I guess, in this case. But using CSV files is always safe. Then on the other hand, the XLSX format that they use here can do 1 million rows. So for now, that's enough, because in this data set, every row is a date. So for each date, you get for each country the current figures. So we're not yet that extended into the pandemic that we already have 1 million dates available. So we should be fine. Although we also thought we should be fine in the year 2000, in the years before that. So never assume. But for now, I guess the Excel format would be safe. Yeah, so yeah, but what I did, I just fired up a notebook, and then you have to know that most of the experience that I have as a data scientist until, well, basically until April, was in other environments than Python and Jupyter notebooks. So for me, it was also a learning experience. So I've got quite some experience in data science and analysis. I used just about any tool you can imagine, I guess, starting out with SQL and doing even Rex scripts and what have you at the time. Lots of programming in C and whatever, because before Python was generally available and used as a data science language most of the time. So yeah, I did use Python these past couple of years, but not really in depth and not good enough, I thought, for myself. So I also thought, yeah, let's dive in and see how to use Python for this kind of stuff. And I think that is the right way, I guess, for approaching something like this. People who want to be a data scientist tell me, yeah, I want to be a data scientist, so I'm first going to do a Python course, and then we'll see where we get. I always turn it around and I say, no, don't learn Python. Start on a project and learn the Python that you need for doing the project and for getting to success. And then probably your Python code won't be that nice. And I hope you can comment on that today and tell me that I can do stuff better. But I just used it as a tool. I just said, okay, I want to get more insights into the outbreak of a disease, find out what's going on. And I'm going to use Python for that. So that's and learn it on the way. So yeah, I made all these notebooks more or less standalone. I try to at least. So you should be able to get them into any environment that you use, be that bare bones Jupyter notebooks or Jupyter Lab, which I started using some time ago. Or Anaconda or whatever cloud environment that runs Jupyter notebooks. They try to at least download their own data, and if needed, they install their own prerequisites. So yeah, what I started doing is just at the top of this notebook, I just started using wget to get these files in. There's also Python libraries for that, I know, but this is clean and easy. So at the top of the notebook, I always download the current data, and I check with -n here to see if there's new data available and download that if necessary. So that's where I started. Yeah, and then there's one thing. So I talked to you about trying not to overfit on the local situations by using very many different countries and outbreaks. And the second thing was I also always at the start of my project try to use as little data as possible. And that may sound strange. And then I don't mean the length of the data set, so as many days as I can get, but as little columns as you can use. So, because I always say first start with the facts and start with the data that you have for every country. I could have started looking at, for example, infection rates or hospitalizations figures or stuff like that. But certainly at the time and still, that was not available for all the countries. So if you start building a model and you want to use hospitalization rates in this case, yeah, you can only use the countries where you have that data for, and then automatically you get a bias for that kind of countries. Because, well, typically, let's say that you only have hospitalization rates for Western European countries, for example, then you can only build your model on that, and you get a model that is probably overfit for Western Europe, and you can't use it in any case to say something about other countries. So minimal data set. In this case, I started using basically only the dates, which are a little bit aggregated in this data set. So you use 3 columns to start with, and you can do that from any data set. It's that flexible, I hope. So what you need is a date, a location, and a number. So the data set typically tells you on this date for this location, which are countries in this case, I have this number for newly tested positive cases in this notebook. So yeah, that's a matter of importing the notebook, getting it into pandas, running into all kinds of nice stuff that you always run into when you start using data in practice, like a country which is called Namibia, which has a GeoID NA. And you can imagine what happens when you try to import that into pandas, which sees a column that's called, which has data that's called NA, which is available, but coded as not available. So there's always that kind of stuff. So took me a while to get this imported in the right way. Running some checks, but I'm not going to fully run through this whole notebook. You can do that yourself basically. So in the second hour, pick it up, run it, and tell me what's going on there. So yeah, then there's the matter of getting the data into the right shape for analysis. I always say get yourself into an environment where you can start asking questions as quickly as possible. So in this case, what I did is I pivoted the data into a data frame, which is much easier for querying and comparing stuff. So what I did here from this data set, because there's case and disease data available, I basically created 2 big slices, cases and deaths, which are the values in this pivot statement. I said let each row be a date, so date becomes an index here, which is also great for plotting, as we will see later on. So the date becomes the index, becomes the row index, and the countries become columns. So that's basically what this statement does here. Yeah, which was pretty easy. It was pretty easy until I found out that I had not available columns here and stuff like that, which Pandas really doesn't like, and which turned out to be Namibia. But there you go. Once you have the data corrected, you can get this nice pivot table out of your data. And we will see later on that there's lots of other possibilities of solving this, obviously. But at that time, I just said, okay, let's do it this way. And then you see a lot of not available inside the columns, but that's easy because I mean the country Andorra, which is here, AD, did not report anything for this date, so there's not available there. Afghanistan, for example, did report for that date, but they reported 0 cases. So that's already something that you have to keep in mind. That you could treat the not available here probably mostly as being 0 cases for that day. But then again, there could be suddenly some not available popping up in a time series. While there's lots of cases being reported and suddenly you get not available, then there's probably something else going on there. So pay attention to these values, which you will obviously see when you start visualizing. So yeah, some description of the columns here. I always put a transpose after my describe here, that you get nice a better overview of what you're doing here. Yeah, and then to the first graphs, and yeah, then Pandas makes that pretty easy. You can obviously use Matplotlib directly, but that's a lot of statements usually. So it's pretty easy if you have your data in the right format, like I did, where you can simply start firing off statements like this, where you just say, okay, from my data frame, I want the cases for the Netherlands, and just plot it for me. And then if your index your index is by default taken as the x-axis, so it's pretty easy to start drawing plots here. So first thing was just to reproduce the curves and the graphs that you saw all over the place. So yeah, that makes it pretty easy. If you simply do US here, then you get the plot for US. It's that easy. So you can start asking questions and looking at your data. First thing that you see here, there is a very clear weekly reporting pattern here. So yeah, we solved more or less, or at least we looked at the data problems. Then the next thing that you encounter when you start looking at your data, obviously, is the reporting process that produced this data. So you also have to find out what's going on there. So I was wondering here and looking at data, and it's for just about every country, you see that Tuesdays are peak days. And when you read up on that, you find out that most of the cases for the weekend are usually reported on Tuesdays. So that means that you already have to do some smoothing on the data to get to the right results. Because yeah, very naively, if you just run a time series on this, which I did, and especially at the rising stage, yeah, then everything that you get out of that will be just a simple prediction where the time series tells you, okay, next Tuesday will be higher than the other days because that's usual on Tuesdays, and it will also be higher than last Tuesday because that's what was going on that at that time. So you really need to do some more data engineering, some more feature engineering to really find out what's going on in a country like this. Because your time series, if you just run it here, it will never predict this kind of graph. I mean, that would just not happen. So there's quite some of your own intelligence that you have to put in here to find out what's going on. So yeah, to scroll downwards a little bit, so there's quite some stuff here. You can look at, obviously, if you want to look at other stuff, you can look at deaths here as well instead of cases. So if you just select the deaths data here, you see a totally different pattern, and you see that the weekly reporting pattern in disease data is even stronger. So you have to take that into account. So lots of examples here. So have a look through it. You see weird reporting spikes, in this case for China, and you can see what was going on there. You can easily do logarithmic plots. You can put a lot of countries inside one graph by just giving it a list of countries that you want to plot here. You can do logarithmic scales, so options enough. So play around, have a look, and see what you can do. So you can do relative cases. You could look at the doubling rate. But yeah, back to the beginning, thinking of my wife working in the hospital and thinking about the load that we are having on our healthcare system, I was thinking, yeah, and everybody at the time was talking about flattening the curve. Yeah, the next question then is, well, I can see the curve now, and I can query it for lots of countries. But what is that curve? And if you're talking about flattening it, what does that mean? Why is a flattened curve different than another one? And how does that look comparing countries? So yeah, then you have to think about this curve. And in the beginning, you saw a lot of people trying to fit the typical bell-shaped curve to this data. And that worked pretty well in the rising slope of this curve. But if you look at if you look at what's going on afterwards, you see a couple of countries, and you see, for example, corrected data for China. So have a look at how that works by taking a rolling window over the data. But if you look at the curve, you can see, okay, the rising one is maybe can be described by a Gauss curve, by a logistic curve, but you can always see that the downslope is always longer. So that it's a longer tailed distribution. And yeah, you even saw specifically for the US a while ago that that was in April, where people said, okay, if we are inside this bell-shaped curve and the downslope looks the same as the upslope, we will probably end up around 60,000 deceased for the US. Yeah, obviously that didn't work. Didn't work for two reasons. Which is what we'll be looking at right now. Two reasons. One, it's not a bell-shaped curve. It's not symmetrical. The downslope is longer than the upslope, so that's one thing. And the second thing is there will obviously be something happening after this first huge wave that we saw in lots of countries. So you can already see stuff happening here during the summer, which there are some local peaks. And yeah, and then most of the countries, unfortunately, are now at least for the number of people tested positively, and I know there's a big discussion there, so we can have that as well. But at least for the people tested positively, you can see there's a steep rise now, and there's lots of countries who are testing much more cases right now than they did in April, and obviously therefore finding much more positive cases. But yeah, it is on the rise, and that is worrying. I mean, even if you're testing much more here, it's rising, and the number of tests isn't rising that fast as the graph is. So yeah, we're getting into trouble again, or are already into trouble. At least in the Netherlands, there's already usual healthcare that's being scaled down to take care of corona patients. So something's going on. So the shape of this curve, and yeah, there's more than one. So how to deal with that? Yeah, then I went deeply into curve fitting. Which is something that I had never done before. So I really had a look at how does this work. And there's all kinds of curves that you can use to try to make sense of this. So I looked at Gauss, obviously, first, which is the symmetrical one. I used it gamma. There was people talking about Gompertz curves. So I really dived into that. And then I found out that if you look at this kind of data in a little bit different way, you're not looking at the classical infection model, where you basically look at what is the infection rate and how high is the chance that somebody gets infected on a certain date. So how high is that probability? You have to do all kinds of assumptions about the underlying model and about how many people meet other people and stuff. So you really have to make a more or less a model of society to do that right. Which is something that quite some countries tried. I mean, in Sweden, they had this model where they tried to model just about every citizen in a model and try to predict what the behavior would be, and then how high the probability would be that somebody would get infected and stuff like that. But obviously, I mean, people were already doing that, and I was thinking, can we do this differently? And then I was thinking about a lot of work that I did in predictive maintenance. In predictive maintenance, what you do is you don't look at the probability that a machine will be breaking down on a certain date, but you will mostly be looking at the distribution of the time to failure. So you say, okay, I'm going to put this machine on the floor in the factory. I'm going to switch it on, and I've got maybe 100 of those machines, and then I can look at the distribution of the time to failure, and I try to model that. So what I did is I tried to model this kind of data in the same way by saying, okay, I'm considering that if you put a person in a society in certain circumstances, he's going to work or not, or he's working from home, or he's meeting his children or not, or he's going to parties or not. According to the circumstances, there's a certain probability that there's a time to, well, in this case, time to infection. So I used that approach and not looked at the daily probability, but looked at the time to infection and the distribution that fits to that. Then after quite some research, and that is maybe a little bit of the science part of data science, although I don't consider myself a scientist. People call me a data scientist, but I guess that's something else. Anyway, I ended up using this distribution to approach the data, which might be one that you've never heard before, because that was the same for me. I had never heard of a Gumbel distribution. What the Gumbel distribution usually does is it models extreme values. So if you look at, for example, temperatures in a country, and you gather the maximum temperature for each year, so you have that kind of data set showing the maximum of a underlying probability distribution, and you draw the distribution of those maximum values, then you get a Gumbel distribution. So that's what I used here. And yeah, I talked to quite some people who do have some knowledge about epidemiology and virology. And I considered this useful because I said, okay, if you consider the daily probability of getting infected as your underlying distribution, and you say, okay, the maximum of that is the amount of time that you get infected. So that's the maximum of the daily infection probability. I considered that proof enough that you at least could try if a Gumbel distribution would fit. And I see the remark that somebody says, okay, this reminds me of Weibull. Actually, Weibull and Gumbel are variants of the same kind of family of distributions. So yeah, it's very much related to predictive maintenance. And then again, Gumbel distribution is used all over the place. So there's quite some knowledge about how that works, because it's also used for predicting earthquakes, because that is also something, it's usually for extreme values. Related stuff is also used in risk analysis, for example, where you usually say, okay, the small risks are happening often. That's what you see in the distributions here. And the large risks are not that often, but they are much larger in this case. Yeah, somebody says, did you try with Weibull too? Yeah, that is the not science part of my work. That I took the assumption that Gumbel would work, and I just started trying it in practice, and it worked wonderfully. That's basically my answer. So that I didn't try if Weibull would be better in any case, because I could explain the usage of Gumbel. It worked good in practice, and it was pretty easy with a bit of high school mathematics, to be honest, to find out how I could fit this in a proper way to the data. Because the formulas for Gumbel aren't that complex. It's basically just the cumulative function of Gumbel. If you look at the cumulative cases in this case, it's basically just a double exponent. I'm not sure if you can read that. I'll enlarge it just a little bit more. So the cumulative is just a double exponent of a linear function. Yeah, and that made it, yeah, I thought, okay, if I'm going to use this one, then basically what I have to do is just take the cumulative daily reported data, take the double log of that one, and then I should have a line. So that is basically what I did here. So the curve fitting with this kind of function can be easily reduced to linear regression. So you take the cumulative distribution, you just take the logarithm twice and take care of the minus signs there. And then you end up with something that should look like x minus mu divided by beta, which is a line. So that was my first assumption. And then I just tried that basically. So I have this notebook available, which is, I don't think I've put it in the PyData folder. We can have a look at that, which is this one. Where it's just one folder up, so you should be able to find it, and that's what I explored in this notebook. So somewhere around here you will see this function reduced to a line. There you go. And if you just do the double exponent of the cumulative data, you end up with a line, which is the blue data, and I just fit a line to that. And then if you have the formula for that line, you have the right parameters, and you can simply double the exponent. You can do the exponent twice again, and you should get a curve. That was basically the approach that I used. So if you do that for just the first outbreak for the Netherlands, for example, you get this kind of results, where the blue is the raw data. The orange one is the smooth data. I took a weekly average window over the data to take out these reporting effects. The orange one isn't that visible, but it's in there. And the green one is my fitted curve. Yeah, and I obviously started doing that for all the countries and all the outbreaks that I could find. Well, you can already see from the linear regression here that it fits almost perfectly. So yeah, the curve fits this outbreak curve also in a very good way. Lots of statistics behind that. You can have a look at how well it fits and stuff like that. But believe me, I tried a lot, and it seems to generalize here. Yeah, but then the problem cropped up of multiple outbreaks because, yeah, you can already see here for the Netherlands, it's very nice that you can fit this first wave and tell something about it. And you can already fit it on the upslope here and tell a lot about what's going on. So you could try to fit this second one or third one, even if you look at the data. Maybe there's already an outbreak somewhere here. So how to deal with that? Then I really dived into the formulas for Gumbel again. I derived a relative measure for the data. So I said, okay, we're not going to look just at the cumulative data, but we're going to look at the new cases related to the total until then, because that's a number you can compare across countries. You get a kind of relative number. And how would that work? Well, the nice thing was if you calculate that with using the Gumbel distribution, you get something that you can easily reduce to a series of lines. So then I got into trouble a little bit because I said, okay, for now I just did linear regression. I could reduce this to a line, fit a line to that, and calculate it back to this according curve. But now I need something that can detect a lot of lines. So I found this one, discussing it with a colleague as well, which is called multivariate adaptive regression splines. The acronym is MARS, as you see here. And you'll see that back in the code as the Earth library in Python, because the algorithm isn't trademarked or patented in any way, but the name is. So nobody can use the name Mars because that's trademarked. So the open source implementation of Mars all over the place is called the Earth, which is a bit of a joke, but that's why the Earth library is in there. Okay, so this one, but what this does is this is able, if you have data that really consists of a couple of lines, you can use Mars to find out the parameters for all these lines. So it's basically a multiple regression model. And yeah, if you look at it related to machine learning, basically, you can consider it as a clustering algorithm. So what Mars tried to do is it says, okay, I've got this cluster of points here, and I'm going to cluster that into this line piece here, and I've got another cluster of points there, and I'm going to cluster those into a second linear part of the data. Yeah, and then you get into all the usual stuff that you have with clustering algorithms. There's lots of other clusterings you can imagine here too. So what it does, it assumes that it's a series of lines. So you have to have data, obviously, that fits there. But then again, yeah, you could do all kinds of clusterings. I mean, you could also do just straight linear regression here and get one line for this whole data set, which then wouldn't fit that well. And otherwise, you could, for example, draw a line between every of these 2 points and get as many lines as you have data points, which is also a feasible clustering. So what Mars tries to do, which is parameterized, and you'll see that I try to find the right parameters for most outbreaks that I've seen in all over the world to get this right, basically. But yeah, there's still this clustering problem where you always say, and that's also in marketing. I've done lots of marketing where you do persona and trying to cluster the clients of your organization into clusters. Yeah, you could consider all your clients in one big cluster, which is a way of looking at it, but it doesn't help you very much. On the other hand, you could try to cater for every client individually, which is also feasible, which is also a good clustering. But that also doesn't help you very much. So you also have to strike the balance between putting everything in one big cluster and treating every case individually. So that's what we're trying to do here. And that, yeah, obviously there's quite some stuff to say about that. And that also makes the analysis in the end sometimes a bit inconsistent, because yeah, I dived into the Earth algorithm or the Mars algorithm to try to find out how can I consistently fit a series of lines to the data. that doesn't always work that well when new data comes in. So that's still something to be analyzed basically. But okay, I said if you use this approach, you can probably get to know more about your data than just staring at this full graph. So that's what I implemented in this worksheet, which then installs its own PyEarth implementation. Luckily, it's available through sklearn. So I call it directly here, but at least because of that, you can easily install it. So that's what this notebook does. So I would basically invite you to have a look at that yourself. I will scroll a little bit through it to tell you what's going on. But before we do that, I can show you a typical output of it, because this is what then finally comes out. So now I've got the UK here. You can simply fill in other countries here, and this is how it fits the curve for the UK. So what it basically does is it finds this big lump of data at the beginning that can be more or less fit into one curve, and you can already see. Probably, if you look at it more fine-grained, you could do multiple curves here. And it would fit even better, but then you get into how useful is that to look at all these individual outbreaks. So basically for the UK, the optimal fit, I would say in this case, based on the parameters that I chose, would be one big lump in the beginning and then some smaller outbreaks. So things were going right. So there were other outbreaks there, but they didn't get out of hand. But then, obviously after the holidays, people came back into the country, or maybe there were measures were released here in this period, so you can see that new outbreaks are starting there. So that is basically what you can get from this graph. So what I try to do is find out the underlying outbreaks, just looking one level below the whole curve, and trying to see what you can get from those insights. So how do you use this? How does this tell you anything about caseload and stuff that happens? You can obviously see changes in policy here. If people start testing more, or if people start behaving differently, or if a lockdown is introduced, you can see if that influences in any way the way that new outbreaks look. And you can try to learn from it if you try to make sense of these underlying outbreaks. So for example, if I look at the Netherlands, you can see outbreaks that are starting, for example, 1 week after Mother's Day, 1 week after Easter, 1 week after we had a long weekend, the Whitsun weekend, where there was also a lot of demonstrations. So I can't say that these outbreaks are caused by those demonstrations, but at least there's a time relation between those. And you can see after the holidays, you can see if you look at more detail, which we will do after this, at regions in the country, you can see that typically where students are returning to their homes, you can see that there's huge outbreaks in those cities, even if they weren't hit that hard in the beginning of the year. So you can try to make sense of what happens, try to learn from that, and for example, see. I mean, we all know that Christmas will be coming at the end of December. So if you look at the well, let's say the Easter-related outbreaks in lots of countries, perhaps you can learn something about that. I see a couple of questions in the Discord, which will have a look at. Seasonality. Well, seasonality is obviously something that comes into play when you look at it over years, I would say. You can see a clear difference between Northern Hemisphere countries and Southern Hemisphere countries in the way that the outbreaks proceed there. So I'm not going to say that that is caused by seasonality, but because it could also be caused by simply that those countries typically take other measures or behave differently. But yeah, you could try to say something about seasonality by analyzing these graphs, I would say, and the underlying outbreaks. Let's see this. Yeah, well, so indeed, there's lots more to say about this. I mean, I'm just scratching at the surface of what you could try to do with this kind of analysis. So seasonality is typically a big part of this. Then there's a question which if I would be able to fit all the outbreaks with different linear regressions created by Mars. That is basically I can't say yes to that easily, because I don't know if I caught all the outbreaks. But yeah, I get good figures in my overall fit. let's say, of the underlying outbreaks that I detect, if I relate them to the full number for those days. And in these graphs, the blue background is the actual data. The pink one is my model, which should then very well overlap the blue one, basically. Yeah, there's a difference, obviously. And you can see the effect here at the end of the data, that there's a big spike here. That can either mean that there's a lot of cases now breaking out here. But I know for the United Kingdom that based on this Excel glitch that we just looked at, that they didn't report the cases for last week and the last couple of weeks fully. So now they suddenly report all those cases in a couple of days. So probably this spike is just a data spike, but it could also mean that cases are very much on the rise. I mean, there's not enough data here to statistically reliable fit another curve to this one. But usually what I see when you see this kind of outbreak or this kind of effect in a country, that in the following days there will be a new wave fitted to that. And that could be a huge one. I think we have I have some examples for local data where you can see that happening. Yeah, there's a question about any way to quantify the increase in testing and adjust for it. Yes, there is a way. Obviously, you can look at the testing figures for countries, which are more and more available now. In the beginning, I didn't have that at all. I couldn't even see how many tests there were. So the only hard data I had was positively tested cases. You could also say, yeah, the deceased figures are more reliable. But even there's a big assumption in the disease figures. I mean, what is a corona death? That is a definition that you can discuss for days, and lots of countries have a different definition of what a corona death is. For example, in Belgium, they say, okay, if somebody is suspected of corona and then dies, and we didn't even test him, we count him as a corona death. So they have a huge death figure. Which is not because that is actually more people are dying there because of corona, but because they measure it in a different way. So that's always a problem. At least I assume that over the outbreak here, that testing circumstances were more or less constant. And what I've seen happening is that when a country suddenly starts more testing, you get, by the clustering algorithm, the data becomes separated into two waves, because then it says, okay, I've got this outbreak that was running under the first testing circumstances, then circumstances changed. So there will be another outbreak, a separate outbreak, and that means a separate linear part in the reduced graph for the new circumstances. So then that is the way you usually see that testing changed a lot. In this case, I know that it did because we are testing much more. The UK is testing much more. So there will be, it's different people that get infected now. So it's much more younger people. So the percentage of people that actually ends up in hospital is also much lower. So yeah, there's quite some stuff you have to take into account in interpreting this kind of data. But at least, so I'm not saying this tells you the truth. I'm more saying this gives you one extra layer of information for research. That's basically what I try to do here. So I'm also not saying I'm predicting here. And I would also say, because I cannot predict a next wave. Basically, I cannot predict that people are suddenly going to have lots of illegal parties next weekend. But I can tell them, I can at least try to fit the current situation and say, okay, if nothing changes, then we will be, this wave will progress in this way, because that's what I usually see happening. So it's also, yeah, one of the basic problems you also always have in trying to say something about the future in these kind of cases, because this is probably not going to happen, because circumstances will change, and other people are looking at these graphs as well, and eventually what you're looking at here is the behavior of people, and that will change over time, and they will react to this kind of news as well. So a couple of weeks ago, or already longer, there was this news article about students returning to their universities in Alabama, and there were 30,000 students going back to university, and within a week they had over 500 infected. So at that moment, when they were just starting to get into this new outbreak, I could fit a huge curve to that, which would contain 150,000 people. But I would almost say, luckily, that didn't happen, because they had already were starting to take measures. They were going into lockdown. They were closing bars. They were very strict on social distancing on the campus. So that wave never happened. Luckily, I would say. So in the days afterwards, this thing became lower and lower, and finally ended up as a wave for about 15,000 people. Yeah, then you can say on the one hand, yeah, your model is crap because it predicted 10 times as much and it didn't happen at all. But yeah, that is how it works. And that has also always been my frustration in all kinds of risk and fraud related projects. That as a data scientist, you're doing your best to make your prediction not true. Because you're saying, okay, I'm predicting a lot of fraud going to happen in the next month for this kind of law or this kind of regulation. And then you tell the government that you suspect that that's going to happen, and then they take measures, and the fraud never happens, or is a lot less. Yeah, and then people tell you, yeah, your model was crap because it predicted all this fraud and it didn't happen. No, it's the other way around. That is what the model was for, to prevent that from happening. So that's always something. Yeah, that's daily practice that you always have to take into account in models like this. Right. Yeah, I see the question. Would it make sense to use different curves based on whether there's a lockdown in the country at the time? Yeah, I try to turn that around and say, okay, I'm not going to do any assumptions about that. I'm just going to draw my curves, and from there trying to find out if things were differently. So, for example, can I find a difference in people returning from holiday in different countries? So there will be a larger or a smaller wave in all those countries. And is that related to them having a lockdown or having quarantine measures or whatever? So it's basically it's the other way around. I try to use it as a trigger to start investigating that kind of stuff. So actually, there is a couple of notebooks as well available, not in the PyData folder, that look at measures related to severity of outbreaks. So I also did that kind of analysis, but yeah, we can't do it all in this morning. So. Okay, right. So what happens? I'll just scroll through it a little bit to when you're later on looking at it. So at the top, it just does the basic thing. It imports its own data, looks if there's a new data available. It does the well-known pivot there. So that's just about the same as in the other one. Then what I do is I extend my data frame by 1 year, so I have room in the data frame for projected values. So that's what's going on in this case here. So you can see it gets extended to October 7, 2021, because the data for today is not in yet. It usually gets available somewhere between 12 and 1 p.m. So it's yesterday's data. You can see here. Some checks here. I define the Gumbel functions here, which are just straight from the wiki page, and then you just get into here. So it is a bit documented, but it can always be better. So what I do is here I create a slice of data where I can start putting my wave data into. So where I try to detect waves. I look at the minimum number of cases. I found out that for large countries, if you try to fit to every day 10, 15, 20 people being positively tested, that is mostly noise for the model. So I usually look at 1 in a million cases for the population for that country. And luckily there is a population count in the data set that I use. And I say, but it needs to be at least 2. If I always look at 1 case or 0 cases, you get all kinds of spurious fits. So I found out that looking at least 2 cases per day is usually works. Let's put it that way. But it's a parameter. You can change that around. So basically, what I do is I create this curve. I create this relative measure here by saying I take the measure divided by the cumulative sum of the measures until then. So this is something that you should be able to recognize. Then I say that this number should be larger than 0 because there's sometimes negative numbers of cases reported. There's all kinds of stuff in the data. I take off a little bit of noise at the beginning and the end of the graph here for fitting. Then I basically take these 2 columns, which is a day number and the number in my data set that should be linear. And I fit an Earth model to that. So here I call the Earth model. There's quite some parameters here that you can change around to find lots of little lines or a couple of large ones. That's basically what you would like to see in your output. So you can say, okay, I want only 3 curves at maximum fitted, and then you will have a general fit which has a lot of error. Or you can say, I want lots of multiple small curves. So that's basically the parameterization of the Earth call here. Yeah, and then there's just a lot of stuff in trying to make sense of the output of Earth. So I detect the line, I detect the knots, which, as they are called, which break the curve into separate lines. And I detect the most suitable line piece at that time to fit a curve to. That's what's happening here. So here's the selection algorithm. There's also lots to it that you can say about that. So I try to find one which doesn't contain too little days. So if I have a line that only contains 2 days, for example, you can have a perfect line between 2 days, but it doesn't tell you very much. So there's stuff in there like that. Here I break out if I don't have any data left. And basically what's going on here is that I find out the slope and the intercept of that line. So I just look at the figures and try to find out what that line would look like. And I calculate for the Gumbel distribution my beta and my mu parameters from the slope and the intercept, which is basically a bit of, I would say, high school equation solving, where you can say, how do I calculate those? So if you're interested, have a look at the wiki for Gumbel. And then I just apply that, and I say, okay, if I found this beta and mu for the Gumbel distribution, I have to scale that back to the original data, because the distribution is always between 0 and 1. So I scale that back to the original amount of data. That's the final number that I get, which is the final number of people in that wave. Yeah, and then I just calculate that back into the data frame. So I just apply this function to the day numbers in my data frame, and get a wave out of that. Then what I do is I fitted that part of the data, so I subtract that from the original data and then run the whole thing again to find the next suitable linear piece to fit a curve to. So basically the whole thing is then just an iteration in doing that. And this is the text output, so you can have a look at what that gives you. So it tells you the according beta and mu values. I do derive some kind of fit measure. Still lots of discussion about that, how you could do that, because there's lots of ways you can do a measure, but at least you can compare them. So there's a couple of curves that don't fit that well as others, at least you can see here. Yeah, and if you have the data, you can see, okay, when did it start? When was the first case in this wave? Oh, sorry, that's the from figure here. When is the peak? So when is the highest load for the country for this wave? When does it end, and how many people are contained in this wave? So basically the output of the clustering algorithm assigned 220,000 people for the UK to this first wave. That's what it tells you here. So that's the output here. And yeah, and then basically based on this data, I just do the plot. So there's just basically a list of curves that I build up while running this iteration. And I just plot them all with a couple of parameters here. And there you go. Then you get this kind of plot. So have a look at it yourself, or yeah, or let's discuss in the coming hour. Yeah, to finish off, I talked to a lot of people about that, and they said, yeah, we need more local data. So that is useful. Obviously, you can look at more local data. So for the Netherlands, I found this data set, which is daily published by the RIVM in the Netherlands, which is the Dutch Health Institute. And they have a daily case file that they publish, where every line is a case, and they even tell you something about that case, like age and gender and stuff like that. So basically, this notebook is much similar to the previous one. It picks up the case data for local areas in the Netherlands, and it does this is what it looks like. So 1 case per row in this case. So we have to aggregate this to daily data, which is something you can easily do. It's just a different pivot statement that's being used here. So there's some stuff in here in getting the data into the right format. Here you can say, okay, I'm going to use as a region, I'm going to use a kind of column here. You can even do the experiment of for example, using age group as region. So you get different curves drawn by age group. So there you can easily change that. So if you simply put age group here in the region variable, it will analyze on that column. So here I do the pivot, which looks a little bit different here because there's because I have to aggregate as well. So I sum the data for a date. So there's an aggregation function in there as well. I say, okay, let's put 0 for every missing value in there. That's stuff that's going on there. So then basically I get the same format as I had before, and I get the for each date for each region in the Netherlands. I get the figure that I'm going to use in my analysis. Yeah, and then it's basically the same code. The only thing that I did is I just put a big loop around it. I said for region in region, so I do this for every region that I find in the data. I go through the whole procedure and create this graph. So basically this is the same stuff going on here, and there's now a big loop around it. So for every region in the Netherlands, it will calculate these figures, and it will output a graph for each of these regions. So there you go. This is, for example, the Zuid-Holland. Zuid-Holland-Zuid even, so that's the southern, southwestern part of the Netherlands, where you get these regional outbreaks. So yeah, you can start seeing differences between these regions. So this is Amsterdam, for example, where there was a huge amount of new tested cases. Let's put it that way. And it's luckily it's already going down, but you can see that probably in one of the next days there will be a new wave probably be fitted here. Let's hope it's lower than the previous one. But yeah, you can have a look through this stuff and see what's going on. You can see even within a region sometimes clear regional effects. So for example, this is a part of the Netherlands where they did not have one big outbreak, but it was basically a couple of smaller regions inside that region that went after each other. I actually did the research and found out that this actually represents what happened there. So yeah, you can see that, yeah, all this talking about second waves, for this region, I already say they're already in their 16th wave. So yeah, if that's useful for your decision maker, discuss it with him or her. And if they say, yeah, we can't do anything with 16 waves, it need to be less, you can change the Earth parameters and try to get a different fit. Yeah, and then the last one, because this whole stuff was about building a corona radar. So in the last 5 minutes, I'll invite you to try this out for yourself. What I basically did, if you have this data for regions and you have this fitted data, yeah, you could put it on a map. I mean, these are regions in the country, so why not put it in a map? So I used Folium for that. Not sure if you have seen Folium before, but I've used it before. Very useful library for mapping data. It uses map data from OpenStreetMap, and you can simply give it a list of coordinates and values, and it will plot it for you. So for a static map, that's pretty easy. I found out there's also an animated plugin for Folium. It's called Heatmap with Time. There's some documentation in the README about that. Yeah, and Heatmap with Time needs a very specific input format. So I spent most of my time getting the data into the right shape for outputting it on the map. So what it does, I created, it reached the output of this previous notebook. That's something that I didn't tell you, but at the very end, it outputs all this predicted projected data for all these regions in an output file, in a CSV file in this case. And this next notebook picks up that CSV file and gets it into the right format for plotting. Yeah, I created for every region these latitude, longitude coordinates. They were not available for these regions, so that was just an hour of looking at Google Maps and finding out the right latitude and longitudes. But okay, that's just work you have to put into it. Luckily for US states, for example, you can get a list of that. Yeah, and then there's just quite some manipulation. So what I obviously do is I tie this output data from my previous notebook, which again has 3 columns. It has a date, it has a location, and a projected value. I tie this to the latitude longitude values I found out myself. So I just merge these 2 files together. That's what's happening here. So here I do the merge. Here I look at exceptions for the merge, something you always have to do. So what I usually do is I say I put an indicator for the merge, and then you can say, okay, if the indicator is not equal to both, So if there's a record in one of the two data sets that didn't match, then output it. In this case, it didn't output anything, so everything was matched. For example, I found out that there's a space behind one of the regions here, so that's the usual stuff. So yeah, there's a lot of data manipulation here to get from this data frame containing values and latitude, longitude values to a list of coordinate values. That is the inputs that Folium needs, and then just calling Folium with those parameters, and this is what comes out. So I'll just put it on a higher frame rate here to make it a little bit faster. And if you then play it, it will simply plot this data on an animated map, and you can see very well how this disease spread and behaved over the country. So now the first wave is gone, first big wave. There comes the second one, and then it really gets bad. And yeah, I'm sorry to say that this is the current situation, projected 1 week ahead. You can see it goes ahead to October 15, but things are not looking good in the Netherlands. So that's basically what you can see from here. But if you do this in more detail, and I've done one for municipalities as well, which has much more detail, but then for some of the municipalities, too little data for a good fit. You can see in much detail how this progresses over the map. Right, so I guess, yeah, well, it's exactly 11 o'clock, so that's good timing. Yeah, I'll be honest, I've been watching the clock and try to end at this time, but because, yeah, by now you can probably gather that I can talk about this for days. So yeah, if you go to the GitLab link that you see, there's an extensive README here, so that tells you how to pick this stuff up and get going for yourself. Yeah, so I would say, go ahead, have fun. I'll be available for the next hour as well for questions.
Yeah.
There you go.
Yeah, so thanks, Damiaan. This is perfect timing. And I was supposed to be taking questions, but you have been taking the questions yourself, right? So I do have a question. How do you do this? You're presenting and doing code at the same time as taking questions.
Yeah, actually you can't, because it's nobody can multitask properly, but it's a matter of because I wrote all the code myself, so I know exactly what's there, so that helps a lot. And I've been doing this for I've been working at this for the last half year or 6 months or something, so the story comes easily. And then I've got time available in my head to look at the questions as well. And I'm using 2 screens, so that's obvious.
That also helps. Okay,
I didn't send any video, but most of the time I was looking sideways, and I've got all my code on the second screen, running inside a VM, a Linux VM, to separate it out from all my other work. So I'm just presenting that content, and I've got you on my laptop screen. So yeah.
Okay, perfect. Yeah, it's great that you've been taking questions already. And yeah, let's see whether we can continue the discussion a bit. I do have some questions myself, which I didn't post already, so I can still ask a question at the end. So I was wondering, have you also been looking into the agent-based models or the network models? Are you familiar with those?
Yeah, I looked into those, but then I thought, and obviously how this would compare to those models, because I mean this is not a replacement for that. It's an addition, I would say. So it would prompt you to look at certain places or certain age groups or whatever in more detail in your other models. So it doesn't replace them. I think it's an addition to that, and I did look into those. To get to know how this stuff is typically done, and then I decided to try and do it in another way and see what comes out. Yeah.
So interesting thing. We in one of our meetups we had also a guest speaker from London from the AI for Good project, and they were mainly focusing on those projects. And I've been involved also a little bit in trying to build such a network model myself. But I think it's a little bit of more simulation-based methods, right? So it is really interesting if you want to model specific interventions, but it's kind of more inside the simulation, right? And I guess what you are doing is more modeling the real data that's out there.
Yeah, exactly. That's what it is. And I found out that there for such a simulation like or a SIR model to work correctly, you have to put in so many assumptions. That I was thinking, I can make up all these assumptions, because you really need to be an epidemiologist to do that correctly, and that's not what I am. So I decided to yeah, to turn it around and use as little data and as little assumptions as I could to see if you could already find out something by doing that. And yeah, I think I did. Yeah.
Yeah. Yeah, you certainly did, and we saw a lot of great code. So thanks very much for the talk, and for all the attendees, you can continue looking into the code, and Damiaan will be available in the Discord channel, so we can continue the discussion there. And also afterwards, we have the lunch break, and we hope to see you back for the interview with Corinne. We are very much looking forward to it. Just to shortly repeat, she's the founder of TomTom and the Codem coding school, and they have a pretty unique approach in learning students how to program. So please start looking into the code, join the discussion, and we'll see you for the interview with Corinne after the break.